Hello everyone, my name is Haipeng Cai from Washington State University. I hope you have been staying well and safe, and thanks for checking out our full presentation on a journal first paper. In this talk, I'm going to share our work and thoughts on a new performance metric of malware detection called sustainability. When it comes to mobile software, Android is still the dominating platform, and this is true in terms of the mobile operating system installed on mobile devices, shipped around the world, and the mobile platform on which people use various Android mobile apps for various purposes. For instance, in the third quarter of last year, more than 85% of all smartphones shipped around the world run Android, as shown in the top chart here. Sadly, but kind of expectedly, not only is Android dominating in the smartphone market, it also holds the majority, up to 99% of mobile malware. Malware in Android indeed seems to be really hard to tame. On the one hand, numerous and a continuous growing number of approaches to Android malware detection have been proposed and published. Just in this year alone, by this time, thousands of papers have been published on this topic, according to Google Scholar. And the vast majority of these approaches are based on machine learning classification. Meanwhile, the malware in Android is not getting any fewer. In fact, the number of new malware samples in Android is still fast growing. And the main cause, as we and many other researchers found, is evolution. Indeed, Android evolves rapidly. As evidence, the platform SDK of Android has had 28 versions in just less than 10 years. The evolution leads to deterioration in malware detection. Features relying on the characteristic of one version of Android that were used for detecting malware in that version becomes ineffective when applied to apps in later versions of the platform. And the chart here shows a state-of-the-art Android malware detector called Mamadroid deteriorated rapidly in terms of the accuracy when it is applied 1 through 5 years later after being trained. While evolution is the cause of the problem, it is inevitable since any successful software has to evolve constantly. We see evolution as an opportunity to address this problem. In this work, we propose to use evolution as a leverage to study and control this deterioration problem. Accordingly, we introduce a first-class performance metric for malware detection, especially those techniques that are based on machine learning classification, and that is sustainability, defined as the accuracy of a classifier that is trained on samples developed in year X and tested on apps developed in the same or later years. We developed a new detector called DroidSpan that aims at a higher sustainability. It leverages an evolution study of apps to discover evolution-resilient features and then uses these features for classification. We then assess the sustainability of 5 existing Android malware detectors versus our detector DroidSpan against more than 10,000 benign apps and a similar number of malware across 8 years. Our study revealed a significant improvement of DroidSpan over the 5 existing malware detectors. In terms of sustainability, this is an overview of our work. Next, I'm going to elaborate on each of these parts. We just have sustainability described as the accuracy of a classifier trained on apps of year X and tested against apps of either the same or later years. More specifically, we define sustainability formally through 2 metrics, reusability and stability. The reusability of a classifier is measured by its classification accuracy in an average case when trained and tested on apps of the same year. Essentially, these accounts for how well the classifier can adapt to a new population with retraining on new samples from the population. The stability of a classifier is measured by a tuple, including the classification accuracy it achieves in an average case when trained on apps of year X and tested on apps of a later year, and the number of years between the ages of the training and the testing data. So those are the 2 parts of the tuple that defines stability. And this metric essentially indicates how stable the classifier is without retraining or any other model updates. Aiming at a detector that provides superior sustainability over the state of the art, we developed the DroidSpan, a dynamic detector based on supervised classification. Just like many other learning classification-based detectors, DroidSpan trains a binary classifier based on predefined features and then classifies an unknown app as benign or malicious. The key difference that would lead to a higher sustainability is about the features that it uses, which are different from existing state-of-the-art techniques. Specifically, it leverages an evolution study of apps to discover evolution resilient features. That is, the features that constantly differentiates benign apps from malware over time. We found 52 such features after exploratory experiments against a relatively small but multi-year dataset of sample apps, and we call the collection of these features extracted from an app the sensitive access distribution or SAD profile of the app. It is named so because all these features are about sensitive accesses in an app. And these features fall in three classes, each addressing a different perspective. The overall extent of sensitive access in terms of total sources and sink invocations, the characterization of invoked sensitive access in terms of the categories of data retrieved by the calls to sources, and the categories of operations performed by the calls to sinks. And finally, the method level control flows that potentially carry out execution passes reaching to sink calls from source calls. All features are consistently percentages of calls in one group over those in total. We use these relative statistics instead of sheer numbers in order to capture the general patterns of app behaviors regarding sensitive access. Constructing the SAT profile of an app is reduced to extracting the 52 features from the app. And the figure here depicts the workflow of the SAT construction process. First, the app is instrumented for tracing. To overcome the vulnerability of static analysis to code obfuscation, we probe for invocation of all methods in the ABK bytecode, including those in the exception handling constructs, such as catch and finally blocks, and those invoked through a reflection. We do not recognize source async APIs in the source code during instrumentation. Instead, all call sites are probed for monitoring the core targets, and the source async calls are recognized later only from the call traces. Second, the instrumented app is exercised with automatically generated test inputs for T minutes on our device. And we currently use T equals to 5 to balance between overall cost and the trace coverage. And we experimentally tried through a few other values of T, and we found that 5 appears to give the best balance. Lastly, all the SAT features are computed from the collected traces. To validate the sustainability merits of DroidSpan, we are applied to more than 10,000 benign and malicious apps across 8 years with roughly balanced sizes across the yearly datasets. Some of the apps we started with were not included eventually because they were either not instrumented or profiled successfully due to problems like broken APKs or missing asset files in the APK package. And this is both an evaluation study for DroidSpan and extensive and first-of-the-kind assessment study of learning-based malware detectors focusing on sustainability. We chose 5 state-of-the-art detectors at baselines, including a dynamic detector authored by Alfonso et al., and we named the detector so by the author's name. We assessed the existing techniques and compared them against the DroidSpan in terms of reusability, stability, which together define sustainability, and the efficiency of these detectors. To evaluate reusability, we conducted 8 rounds of training and testing each using the benign app and malware datasets from the same year. For example, B10 plus M10, meaning benign apps of year 2010 combined with malware of the same year. Specifically, we randomly selected a third of samples from each class, malware or benign, and reserved them as unseen or novel samples for testing, while the others are used for training. We found the results show that in terms of reusability, DroidSpan averaged 94% across the 8 datasets with small variations, which is 6 to 32% higher than any of the baselines. And we further performed a 10-fold cross-validation, which showed similar advantages of DroidSpan. To evaluate its stability, we conducted 28 rounds of training and testing, each using the benign app and malware datasets of year X for training, and those of year in X plus 1 to 2017 for testing. For example, training on benign 15 and malware 15, and testing with benign 16 and malware 16, as well as benign 17 and malware 17, respectively. And we have just 28 experiments. Here, let's just see the results of 7 of these experiments. The figure here depicts the performance results of the test in which B10 plus M10 was used for training. And the samples in each of the following 7 years were used to test the trained detectors. And we can see in any of these 7 experiments, DroidSpan clearly outperformed any of the baselines in terms of the F1 accuracy. In fact, this was true for 25 out of the 28 in total experiments. Grouping these 28 experiments by the number of years between training and the testing datasets ages, we obtained 7 groups. And this plot here shows the group average F1 of DroidSpan versus the 5 baselines. Among these compared detectors, DroidSpan noticeably outperformed all the 5 baselines in terms of stability at any span. Overall, DroidSpan improved over the baselines by 21 to 37% in terms of average stability. Over all the groups, the comparison in terms of overall average of stability highlighted the sustainability improvement of DroidSpan over existing detectors, with 72% versus the highest of 50% among the 5 baseline detectors. We further performed some statistical analysis to measure the significance of these improvements, and we found that the improvements were statistically significant and large based on non-parametric hypothesis testing and the effect size measurement, both in terms of reusability and stability. And we also evaluated the efficiency of all the 6 detectors compared in terms of the time spent by each technique for feature extraction, which is called feature time, and machine learning computation time, which is we call here the ML training time on each single app. The storage cost concerns the space needed for storing app features, and optionally, only for dynamic approaches, specifically the runtime traces. As expected, dynamic detectors are generally more costly than static ones, mainly because of the time for exercising the app for some number of minutes. Nevertheless, DroidSpan had a reasonable time and storage cost, actually better in some cases compared to the 5 baselines. So why did DroidSpan perform better in terms of sustainability than all the 5 state-of-the-art malware detectors? Well, intuitively, the reason a learning classification-based malware detector deteriorates is because, with respect to the features used for the classification, the training samples have a different distribution from the testing samples. When the testing samples are developed in years later than the training samples. And this phenomenon is called concept drift in machine learning. Since the concept drift is not necessarily monotonic, the deterioration of the classification performance of learning-based malware detectors may not be monotonic over years either. And the key takeaway message is that the use of features consistently differentiating malware from benign apps over the years is essential for sustainable learning-based malware detection. And these features can be learned from studies on app evolution. With a relatively intuitive and small set of features, DroidSpan has achieved superior classification performance due to two reasons. The features underlying DroidSpan were discovered through an earlier study that showed they were able to significantly differentiate malware from benign apps. And second, our longitudinal characterization with respect to these features actually confirmed that they can consistently separate malware and benign apps when both groups evolve. Of course, since we cannot do the evolution study for apps in the future that we haven't seen, this methodology cannot eliminate retraining. Instead, it just delays retraining. For more details, please find our paper published at TOSM earlier this year. Thanks a lot for your time and attention watching our presentation.